Today we're going to be talking about how to find three positive numbers when those three positive numbers have a sum of 100 and when we're trying to find the maximum product of those three positive numbers. So in other words, what we're looking to do is find three positive numbers, which we'll call x, y, and z, who have a sum of 100. So if we say x plus y plus z equals 100, that would satisfy the first part of the question. We're also looking for these three numbers, x, y, and z, to have the maximum product. So we're looking to maximize the product of those three numbers. So if we say product is equal to x, y, and z, where the product is we're multiplying those three numbers together, this is the equation that we're looking to maximize. Since we want to maximize this second equation here for product, we need to reduce it to at most two variables. And the way that we're going to do that is by solving this top equation for one of these variables and then plugging it in to the second equation. So if we solve this first equation here for z, we'll get z is equal to 100 minus x minus y. We just subtract x and y from both sides. Now we have a value for z that we can plug into our product formula. So we'll say product is equal to x times y. Here's where we plug in for z, 100 minus x minus y. Now notice that our product equation is in terms of two variables only, x and y. At this point, instead of using p for product, let's just go ahead and call this a function in terms of x and y. And we'll go ahead and distribute the xy across the 100 minus x minus y. When we do that, we'll get 100 xy minus negative x times xy is a negative x squared y, and xy times a negative y is a negative xy squared. Now, if you haven't realized it by now, essentially we're dealing with an optimization problem, and this is a multivariable optimization problem. If you'll remember from single variable optimization problems, once we got the equation together that we were going to maximize, we needed to take the derivative of the equation. Well, in this case, since we have a multivariable function, we're going to need to take partial derivatives of the function. So we'll take the partial derivative of f with respect to x. When we do that, we'll get 100y minus 2xy minus y squared. If we take the partial derivative of f with respect to y, we'll get 100x minus x squared minus 2xy. So these are our partial derivatives. We're also going to need second order partial derivatives. You're going to need those every time to verify that you do in fact have a maximum or a minimum depending on what the optimization problem is asking you for. So let's go ahead and find our second order partial derivatives. We'll do that up here. We'll say the second order partial derivative of f with respect to x. We'll start, remember, with the first order partial derivative with respect to x and take the partial derivative with respect to x again. 100y will drop away because there's no x variable involved there. We'll just be left with here negative 2y, and our negative y squared will drop away because there's no x variable involved. Taking the partial derivative of f with respect to y is going to give us 100x here will drop away, there's no y variable involved, negative x squared drops away, and here we're just left with negative 2x. Now if I take the mixed second order partial derivative and I have x, y, like this, I'll start with my first order partial derivative for x, but this time I'm going to take the partial derivative with respect to y. That's going to leave me with 100 minus 2x minus 2y. I'll come back to these in a second. I'm going to need them later. But for now, what we're looking to do is use our first order partial derivatives to find critical points of our function f of xy. The way that we're going to do that is by solving this as a system of simultaneous equations. So notice this first equation, the partial derivative of f with respect to x, we can factor a y out of this equation because we have y in each term. Here's what that looks like. We'll get y times 100 minus 2x minus y. We'll go ahead and set that equal to 0. Our second equation, we can factor out an x because we have an x in every term. When we do that, we'll get x times 100 minus x minus 2y, and that's going to be equal to 0. Now here's how we're going to find critical points. We're going to find values of y that satisfy this first equation, then we're going to plug those into our second equation to find corresponding values of x. So here's what that looks like. Because we have this factored, we're going to set each of these factors equal to 0 on the right-hand side, take them as separate equations, and solve for values of y. So this equation here, this first equation, is only true if either y is equal to 0 or 100 minus 2x minus y is equal to 0. If y is equal to 0, then we have the value y equals 0, no problem. If we have this second factor here, 100 minus 2x minus y equal to 0, if we take that equation and we solve that for y, we would add y to both sides and we'd get y is equal to 100 minus 2x. These are the two values of y that come out of our first equation. What we want to do now is plug those values of y into our second equation to find corresponding values of x. So if we plug in y equals 0, this negative 2y term will go away and we'll be left with x times 100 minus x is equal to 0. When that happens, we have again two factors here that we need to solve for individually. So either x equals 0, and in that case, we have the critical point 0, 0 because we said that x was equal to 0, and that came from plugging y equals 0 into this equation, so y would be 0 there. Or we have 100 minus x is equal to 0, and in that case, we would add x to both sides and we'd get x equals 100, and we'd have the critical point x is 100 and y is 0 because we got to that equation by plugging in 0 for y. So we've generated two critical points from the value y equals 0 by plugging that into our second equation. What happens when we plug in y equals 100 minus 2x? Well, remember, we're going to plug it into this equation here. We would get x times 100 minus x minus 2 times, here's where we plug it in for y, 100 minus 2x, and that's going to be equal to 0. Now, if we want to simplify this here, we get x times 100 minus x minus 200 plus 4x, and that's going to be equal to 0. Simplifying here, we'll get x times negative 100, negative x plus a 4x is plus 3x, and that's equal to 0. So again, here we have two factors that we have to solve for individually. When we plugged in 100 minus 2x, either x is equal to 0, so in that case we would have the critical point 0, then we would want to plug that x value back into 100, because we don't want to call the critical point 0, 100 minus 2x, we want two real numbers. So we plug x equals 0 back into this equation for y, and we get y equals 100 minus 2 times 0. This term goes away, we get y equals 100, so that point is 0, 100. Or we have this second factor here, negative 100 plus 3x is equal to 0. So solving that for x, we'd add 100 to both sides, and we get 3x is equal to 100, or x equals 100 over 3. So we'd have the point here, 100 over 3. To find the corresponding y value, we'd plug this x value back into y equals 100 minus 2x, and we'd get y is equal to 100 minus 2 times 100 over 3, or 200 over 3. If we want to find a common denominator here, we'd multiply this 100 by 3 over 3 and get 300 over 3. So you can see here that our result is 300 over 3 minus 200 over 3, which is 100 over 3. So then our corresponding y value is 100 over 3. So we've exhausted all of our critical point options. We generated 4 potential critical points, but what we need to realize at this point is that the problem has asked for 3 positive numbers. And if we look here at our critical points, what we notice is that this second critical point is out here because 0 is not a positive number, it's just 0, so that can't be a potential critical point. These points are both 0, and we have a 0 value here for y, so none of these 3 critical points here can satisfy the question we've been asked. That means the only critical point that we can investigate is this first one here, 100 over 3, 100 over 3. Before we go on to find our third positive number, we want to verify that this critical point does in fact generate a maximum. Remember that we were looking to find the maximum product of these 3 positive numbers. So what we have to do is use the second derivative test to verify that this is in fact a maximum. Remember our second derivative test, we use the equation for d, and what we do is we plug this critical point into the second order partial derivative with respect to x, so we get negative 2 times 100 over 3, so negative 2 times 100 over 3. We multiply that by whatever we get when we plug the critical point into the second order partial derivative with respect to y. So again, we'd get negative 2 times 100 over 3 here, negative 2 times 100 over 3. And then we subtract whatever we get when we plug our critical point into the mixed second order partial derivative, and we square that result. So we subtract whatever we get when we plug in there, which is going to be 100 minus 2 times 100 over 3 minus 2 times 100 over 3. I'm plugging it into this equation right here. And we want to square that result. Squaring it is part of our second derivative test. So now we just need to calculate the value here. We get here negative 200 over 3 times negative 200 over 3 minus, here we'll get 100 minus 200 over 3 minus 200 over 3, and we're squaring that whole thing. Continuing to simplify here, negative 200 times negative 200 gives us a positive 40,000 divided by 9. Then we have here minus, if we find a common denominator here with this 100, we multiply it by 3 over 3, and we call this 300 over 3. 300 minus 200 is 100, minus 200 again is a negative 100, so this whole thing here is negative 100 over 3. When we square it, we get a positive 10,000 over 9, like this. Now what we have to do is subtract. We can see that that result for D is going to be a positive 30,000 divided by 9. And we could simplify further, but we don't need to, because all that we care about is whether this answer right here is positive or negative or equal to 0. In this case, it's greater than 0. When the second derivative test is greater than 0, we have to look at the second order partial derivative with respect to x evaluated at the critical point that we found. Well, when we evaluate this at the critical point that we found, we get negative 200 over 3. This value is less than 0. When the second derivative test is greater than 0 and the second order partial derivative with respect to x is less than 0, that tells us that we have a maximum value at the critical point we found, which was 100 over 3, 100 over 3. That verifies that this critical point does in fact represent a maximum of our function f of x, y. So we verify that this is a maximum. All that's left to do is find the value of z, because we only have here values of x and y. To find a value for z, we can plug into this equation right here. We get z is equal to 100 minus 100 over 3 minus 100 over 3. If we find a common denominator by multiplying this 100 by 3 over 3, we get 300 over 3, and we can see that z is equal to 100 over 3, because we get 300 minus 100 is a result of 100. And that tells us that our three positive numbers with a sum of 100 and maximum possible product are the numbers 100 over 3, 100 over 3, and 100 over 3.